Okay, is that better? You hear that now? Okay. Hey, as you see, I'm going to be talking about dwarf galaxies. There's a preview of some things I'm going to show from brand new Vera Rubin Observatory observations, and working with students here at San Jose, at UC Santa Cruz, and also at San Jose State to make this work possible. I feel like there's a little feedback. No? So stand farther away from the speaker. All right, it's kind of an awkward spot. Okay, a little better. Okay, great. So this is a nice review paper from Andrew, who's here, and collaborators a few years ago about different interesting topics on dwarf galaxies and how they may or may not have tension with standard galaxy formation and dark matter theory. A lot of different topics here. I'm going to add a couple of my own of different diversities of dwarf galaxies and how whether they have strong, weak, or uncertain tension with theory. So a lot of these I'll touch on briefly, and I'll come back to them later. And a lot of the proposed solution to these, I think my battery's running out or something. Okay, I have to go back to this. Oh, it's not that, it's the Zoom is laggy. Okay, so yeah, sorry, some kind of lag with the Zoom. Go back. All right, so proposed solution to a lot of these is that stellar feedback is solving a lot of these problems, from not having enough observed satellites to dark matter cores, etc. Okay, I'll just stick on that slide. And then one of the questions is, if that is kind of solving the problem in theory, is can we see any effects of that observationally and test what we call the breathing mode? Okay, now it's completely gone. Oh, I think I'm losing the connection. I am, yeah. Switch to the guest. Yeah. You would think, huh? Okay. All right. Yeah, it still says it's unstable. I wonder if I should just go to the direct connection. Oh, you won't get the recording?
People on Zoom, and I think the recording will. Yeah. So you can plug in addition.
Okay. Let's try this again. Right. All right. Let's see how this goes. Yeah, well, can we see any signatures of what we call the so-called breathing mode, where the bursty feedback causes different effects on the galaxies, and dwarf galaxies in particular? One of the predictions here is that these galaxies should kind of expand and shrink on timescales of 150, 200 megayears. There's an image of a simulation there. Is there any evidence for that? It's obviously we don't get a time series of an individual galaxy, but you can sort of do statistical analysis. This is work that from Imami and Ife Luo has also got a paper in prep on this. I don't think he's going to be able to present it this year. But looking at the star formation rates over the same timescales, how that correlates with size, it seems to be consistent with that picture. And Ife has also looked at the velocity dispersion of the gas. It also seems to agree with that picture. But I think we need a lot more extensive tests on large samples of dwarf galaxies to try to see if these sorts of effects really happen, and how do the star formation histories correlate with their internal structure of the dwarfs. Talking about dwarfs, I just want to put it out there. What is a dwarf galaxy? If you saw a picture of it, how would you know? What is the definition of a dwarf galaxy? Everyone has a different definition. I'd say like if you had to put a boundary between giants and dwarf galaxies, some different ideas are out there in the literature. Maybe it's a bend in the size-mass relation, observed quantity, a bend in the angular momentum mass relation, slightly unobserved quantity of turnover in the stellar to halo mass relation. Physically, is a transition region between black hole and stellar feedback. Would you recognize it morphologically or structurally? Do you have disks or stable disks or not? Or do you have disk plus bulge systems that are stable? If you look at alpha elements, does that maybe track some transition? All these different ideas about where you would look at the transition between giants and dwarfs. I think the consensus with most of these is that the stellar mass is sort of 1 to 2 times 10 to the 9 roughly. And there's like kind of the equivalent halo mass. But I think I'd like to see more done as you look at multidimensional properties of the dwarfs and the giants to see where the distinction lies observationally, and then where does that, what does that tell you in theory about the formation. So there are many years, decades of work done on giant galaxies and looking at the properties. We've seen different plots of main sequence, etc. This is just going to show another type of plot, size mass diagram with lots of color-coded by lots of things, by metallicity, alpha age, alpha abundance of ages, and how the surface density of the galaxies correlates with that, and it gives you a lot of information about the formation histories. Well, the same thing has not really been done for dwarfs. They're fainter, obviously, and so doing that same kind of analysis has not been done before. But the good news is that all these different surveys that are online are coming soon, give us a lot of capability to start getting large surveys of dwarfs. So there's been a lot of work done on dwarfs, but it always small samples and restricted environments, and not really the kind of a very broad overview in detail where you can do these kind of inferences. Here's an example of a stellar mass metallicity relation, where you might think that we know what that is for dwarfs. Very commonly, SDSS is used for the high mass end, and then Evan Kirby's work is done on the low mass end. But that work is just restricted to the number of dwarfs we have in the local group, which is a small sample, and at some level it's going to be a biased sample to our specific environment. So you'd like to do it on a much larger sample, lots of environments, and then the interesting thing here is when you start doing that, and of course people have done it with different methods, is you don't necessarily get agreement. We heard from Lisa Cooley earlier about this with gas metallicities. We'll look at this with stellar metallicities. These are different samples, in fact 2 different studies of the Fornax cluster, and they get offsets in their metallicities. So I'm not going to get into what might be going wrong here, but it's definitely not homogeneous data sets where you could kind of make some conclusions about how metallicity varies with environments. Somebody asked yesterday or the day before about angular momentum, so I just wanted to quickly mention that. In giant galaxies, for whatever reason, you can take a simple-minded spherical Cal picture of angular momentum from halo spin and get something that fits with observations. But we'd like to know, maybe that's somewhat surprising, but what about dwarfs? It would be even more surprising if it extended into the dwarf regime, where the physics start getting different. And this depends on whose paper you look at. So there are some indications that it does extend the same. It depends on which components you look at. Also, it looks like there may be a break if you look at just the baryons, but there are not many data points. So I think there's a lot more work to do on this, but it's kind of an interesting area you can start pushing with dwarfs. We need more observations. This is a paper that just came out yesterday morning, looking at, talking about the internal structure and the kinematics of dwarfs from the firebox simulation of looking at how disk dominated they are, looking at V over sigma. And the prediction is with basically as you get down to the dwarf regime, things get kind of blown up and they're not disks anymore. And it seems to be, I don't know that you can really make very robust predictions yet from TNG 50 because of the resolution. What's interesting about this is that if you plot on here some observations, these green points, there's a lot more spread. And in fact, you get some of these very disky galaxies at low masses that are not predicted. So again, this is in the paper they emphasize, well, this is just a restricted sample of observations. So you'd like to have a lot more observational data to compare to the theory. But if that difference holds up, that could be a major input into the theory. Kind of a related thing that people look at is the sizes of dwarf galaxies. And this is another interesting recent theory paper, so the observations here, the size mass, the middle one is observations, and then the two above and below are two different sets of simulations. So you can see the mean value is dependent on probably numerical resolution and your subgrid physics, and neither one of these matches the mean value of the observations. Some simulations probably do that, but that shows that the sizes are kind of a nice metric of your theory. But it's not just the mean sizes, it's also the scatter, and this was also in this review paper. The diversity of sizes is important to match, and this is just an example of local group. The same stellar mass dwarfs gives almost order of magnitude size variation in the dwarfs, and I don't think it's seen in any simulation. So you can kind of move the mean up and down, but you can never get the scatter so far that matches the observations, and that raises questions: is there more physics or more different formation pathways? Or there's been a suggestion from simulations that this could be an indication of self-interacting dark matter, which naturally leads to more diversity in the sizes. And this is a famous example of a part of this diversity in sizes is the ultra-diffuse galaxies that were kind of started being recognized about 10 years ago. Very, very puffy, large dwarf galaxies. And we still don't know a lot about them because they are so faint that they're not very well characterized at the level you would characterize a giant galaxy. They call one of the surveys is literally called smudges because you kind of measure them as smudges in the imaging, and it's very hard to get spectroscopy. So I'm going to come back to that. But moving beyond sizes, I think there's a lot you wouldn't talk about giant galaxies in terms of their sizes. You know about we've heard about spiral arms and bars, and what about dwarfs? More detailed morphologies, which I'll show in the observations we're looking at. This is another interesting theory paper with Fire 3 showing where you change your subgrid physics. It can change the quenching of the galaxy, but also could change the morphology, and there's some size variations in there, but there's also some structural variations. I won't get into the details of what's causing what, but I'd like to see more metrics used both in theory and observation of things going beyond these simple, half-light radius, things that, maybe at high redshift you can measure, but at low redshift you can measure a lot more than that now, especially with these new deep surveys, more detailed quantities, characteristics. So here's just an example of some low redshift dwarfs, and when you kind of look at these or study their kinematics, everyone looks different. You wouldn't come up with any kind of Hubble sequence for them. They range from being compact, down to blue compact dwarfs, up to these large extended objects. The star formation can be in the core, but it can also be in the outskirts. So here's a blue core one, but here's a couple of them where you got the star formation more in the outskirts. So there's a lot of diversity there, and we don't know are they really different lineages of different types of assembly histories, or is it a cycle where you start off here and you kind of migrate around in a loop that this different type, same dwarf would look like that at different snapshots in time. Also, are there regularities in there? These are all dwarf irregulars in the classification, but are there some regularities here that could also be inputs to theory? And also very interested in star clusters, which I'll talk about in a minute. So these things are forming star clusters in these blue clumps. So I'd like to characterize the clumpiness of these low redshift dwarfs. Maybe high redshift clump research could give some input into that. Here's an example of how you can go into a little more detailed morphology characteristics. We heard the other night about Jennifer Lott's contributions to these metrics for giant galaxies, and for dwarfs this has been applied in the Marian survey to the H1, both to the gas and to the stars, and trying to the Gini coefficient versus this M20 kind of concentration index, and start finding the patterns and how that relates to star formation rate, for example. 5 minutes. Okay, I'm going to really have to speed up. So maybe I'll skip over this because Imong after me is going to talk about globular clusters, saying that's another part of the diversity we see in dwarfs. Now start getting into the actual new stuff, the new surveys. So if you're like me, you have a little bit of trouble getting your mind around what all these wonderful new surveys do, how they're different. I'm starting to, as I start working with them, starting to learn learn the different aspects of them. This is a nice triangle plot that shows you can emphasis on depth, area, or PSF. So putting it here in chronological order, the Euclid mission is already running, so it has a lot of area. It has a good PSF because it's in space. Rubin is also starting to operate. It's got area. Of course, it's on the ground, doesn't have the same PSF, but it's deep relative to Euclid. And Roman, hopefully coming very soon. It also has a good PSF and not as much area coverage, but also going deep. So everything has got a trade-off, right? And I'll just quickly put up here the actual numbers, but you could look at those later on the slides. Just to mention, there's also the whole spectral dimension, which is not covered here. There are some low-resolution spectra in those two space missions, but for example, of course, DESI is all about spectroscopy, and not as well known, but operating now is the Sphere-X mission, which is sort of you could consider a low-resolution spectroscopy, all-sky mission, less depth. Okay, globular clusters, maybe I'll just skip over this, but basically with these, a lot of the aspects combining the different wavelength coverage, depth, and good PSF of these missions, you can start studying up to millions of globular clusters in the nearby universe, just kind of a game changer in studying these statistically. And just a quick snapshot of where we are in these surveys. DESI is, I guess getting close to being done. Euclid is well on its way. Rubin is still kind of in a quasi-commissioning phase, and it's working on this area here called this SV area, about 20% of the way through. So that's kind of just giving you an idea of where they're at. They're at about 1% of the data released here, 20% in DESI, tiny fraction of the Rubin data released. There's a fair amount of data from Euclid released, so we have a survey now on dwarf galaxies with Euclid using about 6,000 dwarfs. It may not sound a lot compared to Sloan samples of giants, but the point is this is kind of a game changer in terms of spatial resolution and depth and everything else. So we're over a large range of environments. So stay tuned. We'll hopefully have results coming out in the next few years on that. With a lot of different science goals, the internal radial metallicity gradients and stellar star formation histories of dwarfs, how it relates to environments, looking at UDGs versus classical dwarfs, and distance measurements, globular clusters. Maybe I'll skip over the DESI survey. That's not, except just to mention the student here, Janet Blanco. Hopefully we'll have results out soon. There's a whole new dwarf survey happening as part of DESI. This is one of an interesting galaxy we found in DESI with Subaru imaging that actually may be a progenitor of globular cluster-rich ultra-diffuse galaxies. It seems to have massive star-forming clumps. So Imong here, you could talk to him more about that. We hopefully have a paper coming out soon on that, but maybe I'll skip over this and just get to one. Just a lot of interesting things we're starting to find as we look at these surveys when you get much greater depth and spatial resolution than you had. I'll just maybe emphasize this one. We actually have a paper out, the first extragalactic paper from Rubin data. This is a ultra-diffuse galaxy. It just looks like a smudgy thing in legacy data. And here's what it looks like in Rubin DP1, which is 10-year LSST equivalent depth. So you can see it's not just a detection. You have the detailed morphology. You can do n-stellar populations. And that's the same object in Euclid, which is complementary. It's not as deep, as I mentioned before, but then, of course, better spatial resolution, so you can resolve these things that look like globular clusters and start doing analysis of those. And LSST, I call it a UDG discovery machine, will have just gobs and gobs of those over the sky that we can study at fainter surface brightnesses. So I'll just skip over. We did SED fitting on this to look at a star formation history. This is another UDG, I think this is the last one, from the Virgo first look imaging from Rubin and in the Virgo cluster. And you can see you've gone from something which is just a little smudgy thing that you can actually do isotope fitting and probably could do some follow-up kinematics to look at this thing in detail. This is ellipticity and A4 higher order moment. You've got a disky, flattened central component and then a boxy round outer component. So this 2 or 3 component structure here for this UDG has gone beyond just being this fuzzy blob where you just have to explain its size. And now we have a detailed internal structure, so that could be a target for any theory of dwarfs or UDGs to try to see if you can reproduce that and give you some clues about its formation history. So yeah, just in summary, there's dwarf galaxies have a lot of potential as a test bed for the physics of galaxy formation and dark matter, but the data are not there for large surveys, which are now coming out. And we have results for early results now from all these different missions on dwarfs, finding some interesting patterns. And just following this as a local motto, keep Santa Cruz weird, and so to say, let's keep galaxies weird.
Questions? James?
I just wonder if you could elaborate more on your thoughts about defining with some metric what a dwarf galaxy was versus like another galaxy. I mean, it's kind of an interesting question about whether it's just sort of a semantic thing or there really is something interesting that happens, and I don't know, what are your thoughts on that?
Yeah, exactly. Is there a phase transition between the different galaxies? And I mean, my thoughts are to try to, get the multidimensional parameter space of the between structural parameters, star formation histories, dynamics, dark matter, combine all of those and just see if they really cluster in different parts of parameter space. From an observational point of view, of course, from theory, you can actually look at the different processes and see, what changes in the mass regime.
Quick one?
I was going to say, you didn't mention much about environment, but it seems like many of the paths that people study are very different, whether they collide with something, whether the satellites or you get ablated, et cetera. So can you comment about your ability to tap into the environment for your surveys, or do you have to get extra data for that?
Yeah, that's one of the key things. I maybe said it too quickly, but one of the prime reasons to use these large surveys, you can probe a full range of environments now, that you not have these very restricted surveys. People look at just clusters or just the local group or just the field, but now you've got everything done self-consistently in a homogeneous data set.
Okay, so let's thank her again. And our next speaker is Imong Tang, connection between dwarf galaxies and globular clusters, insights from the Perseus cluster.